So, are we online? Okay. So, welcome to the fourth and final talk of Walter Van's Suijlekom. So, he's going to talk about truncations of spectral geometry. Walter.
Okay, thank you. Yeah, so the topic will be spectral truncation, so in various forms actually. And so let's again go back to the basis. Of which we now know more or less several aspects, also applications to physics, but also inner fluctuations, which is this spectral triple. Which should now be clear. So A is, let me stress one aspect. So this is star algebra acting on, so as bounded operators on H, and D is a self-adjoint operator with certain properties, which I spelled out before. But we'll not do that again. So A, in particular, can be completed, or closed actually, inside B of H to a C-star algebra. And that's sometimes even given as an input of the data, so that there is a dense subalgebra, calligraphic A, inside the C-star algebra, for which the properties hold that I wrote before. With this, we could have a distance on the space of states. And let me recall what a state space is. It's for the C-star algebra. It's given by positive linear functionals of norm 1. Positive linear norm 1. And sometimes you can combine this, that's actually a nice exercise in functional analysis, with what it does on the identity on 1. But this seems to be the more kind of, also if A is not unital, for instance, then that could be the right way to phrase it. So they will have, so this is convex. And if A is, let's say, unital, as I was saying all the time, convex, then this is also compact, which follows from, again, standard results in functional analysis. And as such, it actually has extreme states. Extreme points, and they will be referred to as pure states. And they're like what should reflect points in the space I started with, because I know that for A is C of x, as an example, these spaces are actually well understood. This is probability measures on X, and it's extreme boundary, the extreme points. The pure state space is actually X. Okay, so that's and they would be the kind of the evaluations at points, so the Dirac measures that are given by this. So they're given these pure states inside the probability measures. So that's a way to kind of get back to a space, and this is the game we're trying to play today, to see if we can sort of approximate this geometrical structure. Because the nice thing about this is that I have actually a distance, which I showed before, on states in full generality. By just evaluating the state under the condition that the commutator of such an element, with such an element, is smaller or equal to 1. So the gradient, if you wish, is smaller or equal to 1. And then you can sort of get a control over this distance. So this is the Riemannian distance in the case of a Riemannian manifold, okay, on the pure states. And on the probability measures, it's something else which is also known from optimal transport, which is the Kantorowicz-Wasserstein distance. So there are several kind of variations, but it has to do with the kind of the transport of say one probability measure to another at a sort of a minimal cost.
So does it help you to define distance between mixed state?
Any state. It doesn't matter. So.
Now probability, if it is a non-trivial, if it is not Dirac delta distribution, then it will be will it correspond to something like a mixed state?
But this is classical, so there's no such thing as a mixed state. I think you need to have some kind of non-commutativity, like compact operators or matrix algebras. That's already sufficient, I think. So 2 by 2 matrices. Then you could talk about mixed states, as sort of given by some density matrix, of which indeed you could try to compute a distance. So I don't know if that's meaningful, but it's something one can do and analyze. See, for instance, how far away am I from a pure state? So that makes sense. But in most cases, what we would actually want is that that distance metrizes the weak star topology, so that it actually captures what you usually say about distinguishing points. But that's not always the case. So it could metrize it. So the weak star topology here is, of course, just a pointwise topology on this set of functionals. But you could metrize it with a distance only in certain cases, which is the case here of C of x. It's also the case of if it's finite dimensional, but more generally, it's actually quite a challenge to prove it. So there's a few results in the literature, but it's actually going quite slow. That, for instance, the Porlet sphere has that property. And then it's called a so-called quantum metric space. If you have such a triple, it's even for which this distance is actually giving you the topology of the state space. And there are several examples like that, but it's still case by case. So I said spectral truncations, and it's actually motivated by physics. But if you don't like physics, you could also motivate it from mathematics, but even also quite strikingly by computer science, because one could try to implement this on a computer and model these kind of spectral geometries on a computer, because in principle I don't have to do any geometry anymore in the strict sense, because I capture everything by spectra, operators on Hilbert space, which is actually ideal to do on a computer because it's like matrices, except that it's finite size. So that's the only thing that any kind of model that you put on a computer, is the first task is, okay, how can I make it into a finite dimensional system? And there's a very natural candidate is by just chopping the spectrum of D. So you just look at part of the spectrum and maybe increase it so that you get some accuracy. And so that's the motivation for the computer implementation of such spectral geometries, which was actually done. The physics one is motivated by measurements. So also with measurements we have a limited spectrum, part of the spectrum available. Maybe there's some bandwidth, maybe there's some resolution, so you don't capture all of the spectrum. So what I will introduce is a truncation of the spectrum. So it's by bandwidth or by some resolution For instance, it could be that you have a continuous spectrum. I mean, that's not the case there, but just making it motivation slightly more general. Some kind of resolution that you can distinguish in your spectrum. Or you want to implement it on a computer. So there are different kind of motivations or places where you find such a truncation to be natural. So that's one thing. And the other is that's like with images, or actually in daily life, when you have a resolution in space. So you have a limited spatial resolution. So that's sort of opposite. And I'm not sure if I will manage to get to this description of that one in time today. But it's very similar in flavor, in the sense that it gives rise to the same mathematical structure. And this you should think about in images, or just, I mean, what you can distinguish, what you can separate, image resolutions, or like pixels, that kind of thing. Or some data set that you sort of look at from a distance, or you cannot distinguish certain kind of data points. So these kind of things are actually analyzed a lot, of course, in applied mathematics. So that's where this lies. But let's make this more explicit, and in these two cases, see what you get. So. So if I have a spectral truncation, the best way to view it is by a spectral projection of D. So you take the spectrum of D, and you just kind of project onto some eigenspace. Projection from D. So it's a P lambda onto the eigenspaces with eigenvalue smaller or equal to a lambda in absolute value. Okay, so that's one thing. Then, actually, I need a little bit more space here. Then, what I can do is the Hilbert space. I can, of course, then look at that eigenspace. Okay, that's a closed subspace, so that's fine. So P lambda H. Write it here. So that's a closed subspace, so that's again a Hilbert space. The operator D acts on here because I took it to be the eigenspaces of D. So I could write it as such, but it's also just P lambda D or D P lambda, whatever. It's just the projection. And let me suppose that this is a finite rank. To make it really, what I said was to have this finite dimensional property, so to make it also easier to compute with.
What is this EV less than? What do you mean?
Eigenvalue. Yeah, sorry. So the eigenvalues are bounded by lambda, capital lambda. And so you have this closed subspace. The operator acts on there as a matrix, really. So nothing very spectacular. But now A. So A does not respect that closed subspace. It will typically move out. Okay. So what you have to do is you have to force it to act on this closed subspace. And this we do by compression. Like this. And this compression, this is not an algebra anymore. So you cannot take products. You will end outside. Because that's what happens when you take products. You move outside of the closed subspace. And I will illustrate this with some examples. We see this kind of very clearly and also very concretely. So it's not an algebra, but it's a so-called operator system. So this is not an operating system. It's an operator system. Even though if you Google it, you have to be well, make sure that you're in the right research direction. Otherwise, and it's I will explain what it means, but it's just right for us to be able to talk about all of this. It doesn't really harm us if we replace C-through algebras by operator systems. Okay, that's the first. Yeah?
The set of eigenvalues less than equal to lambda that don't need to be finite or anything, right?
Lambda is
No,
finite.
The
the set of all these eigenvalues less than equal to lambda.
They are
this,
finite.
This collection don't need to be finite.
It is.
Oh, it is.
But that's because I have a discrete spectrum which only accumulates at
Okay,
infinity.
okay, repeat.
Yeah.
Okay, okay. Oh, okay.
Because I have this kind of in the plus plus. It's
Okay.
yeah, you're right. So it's you could also do that, and it. I mean, this is just to make it easier and everything finite dimensional. But you could say, let's just pick a lambda even for continuous spectrum. That could also work. That's fine. Just then you have to think how that looks like. And in fact, we're looking at such objects as well. We take, for instance, my example will be S1, which is already illustrative enough. And I have another kind of project where I look at R. And then you could do the same, but then you have a continuous spectrum, like this e to the IPX. And you could cut it, but then the operator system that you get is actually still quite complicated because it's not like matrices. So. But this is very concrete. This finite spatial resolution is what you get on a metric space, which could be an effect. I think I will do that if I get to this, to make it a finite space X, and it's like pixels. You should think about them as pixels. So some kind of image of which I can only distinguish if these points are far away from each other. So I put a relation, which is like I cannot distinguish. That's the relation. So they're like within the same kind of I'd say pixel if you look at it from a sort of a far distance. So a relation is given by R. So that X and Y is in R, if and only if. So a relation for me is a subset of X cross X. So it's a very general kind of thing. X and Y in R, if and only if the distance is smaller than some fixed epsilon. So epsilon is larger than 0. So this means that if 2 points are close enough, then I cannot distinguish them. So I put them in the relation, so they're related. So this means that, so first of all, so this is symmetric. So X and Y can be exchanged. It's also reflexive. So if X is equal to Y, then the distance is 0. It's smaller than that epsilon. But it's not transitive. Because if I, suppose I would do something like that, that will be the typical example also. Then I could identify these points. Like suppose I have, this is distance 1, and I take some epsilon which is a little bit more than 1. Then I kind of cannot distinguish these points. Okay, every time the neighboring one, I cannot distinguish it from the... So they're related, but this one is not related to that one. So it's not transitive. It's clear if you look at this equation, of course, but so it's a reflexive, symmetric, but not transitive. So it's not an equivalence relation, but it's a tolerance relation. That's how you call it. It's what you tolerate. In a sense, this is a term due to Poincaré. What you would tolerate as sort of an error in measurements, and that's actually not something you want to add up if you keep kind of having different points. Okay, so this will be another kind of place where I find operator systems, because what I will look at is an algebra that is generated. Now let's look at this. Let's look at a space given by the closure of integral operators on L2 of x, and I of course have to assume something about measures and so on, but that will be an assumption, and it should also be compatible with D, so there's a little bit of compatibility in the results needed, and given by closure of integral operators on L2 of x with support in R. So recall that an integral operator would map H to an operator that assigns to x the integral like this. So it just integrates with respect to a kernel. So that's an integral operator. With support of the kernels, this is in R. Yeah. So the support of this kernel, or the essential support, should be in R. So in terms of a picture, I'm going backwards on this board, but so I hope you can forgive me for that. So if you look at the picture like this, so I have X, or X and X actually, then the points, first of all, it's the relation. If I draw a picture of the relation inside X cross X, so just as axis, I find that it contains this axis, just the diagonal, because this is the reflexivity. And whenever I have something here, I would also have it down there, so it's symmetric. And then it's like, it's this epsilon, it's more or less like this epsilon. And the support, so this is the relation. It tells me which points in X can I identify under that relation with the point in X. Okay, so you just look at the picture and you plot it and you see which points are. And they would be in distance smaller or equal to smaller than epsilon. And the support of the K's are precisely along that band. Okay, so that's what I mean with the closure of the integral operators with that support. Now, if you would multiply integral operators, the support will grow, because it's like a convolution product. So kxy and then kyz, then you integrate along y. That support will be slightly larger. So it's not closed under the product. So this is again not an algebra. Not an algebra. But it's an operator system. Well, it's also an operator space, but let me do call it system. Given by the closure of these integral operators. So it's again symmetric, implies that I have an adjoint here. So that's why this will become an operator system. And so I'll explain in one moment.
So the operator system, you mean start closed subspace?
Yeah, and that's precisely the starting point of the actual definition. So an operator system, also because I was talking about this motivation, but now it's time to actually develop the theory, is a star closed, and sometimes people take it also closed, vector space of bounded operators on some Hilbert space. So we call it E. So that's the definition. So these are all of that type. So this will be closed under the star, because A is closed under the star and P lambda is orthogonal. This one will be closed under the star because the relation was symmetric. So let's then try to develop a general theory based on operator systems. Okay, so that's our task. It's unital if it contains the unit operator. Now, this may seem like a very meager structure, because it's just a vector space which has some star, and that's it. But actually, that's the fact that there consists of bounded operators actually allows us to talk about all the things I was having before, states, positivity, because, and actually the other view on operator systems is that since they're bounded operators, I can talk about positivity. Notion of positivity inside an operator system. Which is simply that T is in E plus, we call, if this is positive. So that's a positive operator for K and H in H. So it's just what you would call positive as an operator.
Just 1 minute. When you talk about this thing that I cannot have absolute resolution of points,
Yeah.
so it reminds me of the kind of spaces we consider in non-commutative space-time,
Mm-hmm.
where because of non-commutative structure of space-time coordinates, they become fuzzy
Yeah.
in nature.
Yeah.
So this kind of formulation will be can be applied there also?
I think it even, I mean, if you think about the integral operators, they're very close to, for instance, the compact operators that are related to the Moyal plane. So there will be a similar structure appearing. But I would like to sort of, there is a sort of a scale which I take into account, this epsilon. So it's of course similar in conceptually as the things that you do with the non-commutativity. But here it's giving a different structure eventually. So, but it's a good point. I haven't, investigated if there is some relation in the type of approach. But
This Planck scale, for example,
Yeah,
can be
sure,
something
yeah.
like epsilon.
yeah. But it's here I take the view that I would like to understand, and that's also. So you like to sort of be able to vary the scale, to view what is geometry looking like at different scales. So this is what I try to capture. So for instance, by the state space, I will then be able to say, okay, it looks like an approximation of something else. That's the task I have. Yeah. So there's a notion of positivity, and actually there's so that's an order structure. So this is the order, which just means that there's a cone of positive elements in E. So, yeah,
Is it H comma TH?
K, comma H.
K comma
And they're all in H.
K comma TK or TH?
K, comma TH. Ah, you're right. Thanks. Yeah. It should be H, yeah. So we can drop the K. Yeah. Sorry. Positivity is of course this, yeah. Sorry for the confusion. So it's H, TH, that should be positive. That tells me that the operator is positive. Yeah, is that clear? Okay. So actually this notion of positivity extends to matrices with values in this E. So that's a matrix order. So it means that I look at matrices with values in E, and I can talk about a cone of positive elements in there. And they're given by letting M and E as acting on Hn, which is again a Hilbert space. So nothing really changed. I just kind of take n copies of H, consider M and E as operators on there, so, and then again write this positivity. So this seems something that is already there, but the strength here is that this is actually a way to characterize operator systems as a vector space with the star structure, such that there are cones of positive elements. So then you can actually show, that's not very trivial, but that was done a long time ago, is that you have an abstract, it's like with Caesar algebras. Concrete Caesar algebras, they would be acting on some Hilbert space as bounded operators. So you can see it. But there's also an abstract notion of Caesar algebra, which is just a Banach star algebra with a certain property for the norm. Some operators on the Hilbert space, closed under the star. But there's another one, which is abstract, which tells you that an operator system is a vector space with an order structure. Actually, that order structure is a matrix order structure with certain compatibility conditions. And then you can show that that is actually always possible to realize as operators on the Hilbert space. So, so the names to attached, by the way, is Arveson here. So if you want to read more about this, then this is the origin in the 60s. And in the 70s, Choi and Evros, they proved this result I just said. 77, I think, yeah. About this connection between the two. So this is clear that it always gives such an order structure, but you can go back, and that's what they prove. So then you have to, of course, say, what do you mean where they're the same, or they can be realized? So there's a notion of maps, and the maps between operator systems should respect that positivity. So there should be positive maps, meaning they map E plus to, so let's say phi from E to F. They should be positive. So phi of E plus should end up in F plus. So in the positive, in the cone of positive elements. But they should actually be completely positive, which is a stronger condition, which tells you that phi of Mn E plus, so it's Mn of E plus outside, it's not Mn of E plus. So because matrices are rather strange, it's quite difficult already to talk about positive matrices in terms of its coefficients, and so this is why this field is actually quite intriguing.
So are these like results, or these are the definitions?
These are
This is
definitions.
phi to be satisfied with these properties.
This means for phi to be positive, this is what it means.
Okay.
Yeah. And this is what it means if you have this for all n. This is what it means for phi to be completely positive. So that's the notion of a map, and I defined it like this. Isomorphisms, such as the one that would then kind of implement such a result of Choi and Efros, would be ones which are completely positive and bijective, and the inverse should also be completely positive. So this is called CP for short, CP maps. And phi is a complete order isomorphism, or in other words, it's an isomorphism of operator systems if phi is bijective. It's a linear map, and both phi and phi inverse are completely positive. Okay. And you need both. So. Yeah. Okay. So, by the way, if you are in complete order isomorphism between C-star algebras, they're isomorphic. So that's good. So it's the same notion. So phi between C-star algebras. So complete order isomorphism. So if you read papers about this, it quickly gets out of hand. So there's a lot of these kind of UCP maps or UCB, or everything will appear. UCC for contractive. So unital completely contractive and positive, that also exists. And in a lot of C-star algebra results nowadays, this happens. This plays also a prominent role. So there's a notion of so for nuclear C-star algebras, one can actually build up from the inside now a system of finite dimensional algebras, in which the connecting morphisms are not algebra morphisms, but they're actually CP maps. And then still they can say something reasonable about the limit. So complete order isomorphism is isomorphism, or star isomorphism of of the C-star algebra. All right, so the notion of this positivity allows us to talk about states. So that's the first reason why this is the why this seems to be a good notion, a good playground to work with spectral triples, actually. So states on E. So they're just again given by the same formula, phi from E to C, which should be positive, and norm 1. And the norm 1 is just given by some kind of notion of supreme taking values in C, so that's also fine. So as I said, you can capture it also by the identity. So that's even then you don't even have a norm. You don't even need the norm on E. You just need the identity. The states. So this just means the of course the order structure on C is just the usual one of positive numbers, of positive real numbers. So that's just a direct consequence of mapping E plus into positive numbers for states, and it helps to think about this as a subspace. Subset, sorry, of the dual. So these are just linear functionals. So that's the dual, but I should introduce an order structure on this.
Is that E star or
AD.
Oh, okay.
For dual. It's not always the Banach dual, but because I want to stress that it has some kind of order structure. I mean, it will in many cases, but
So you're taking all functions.
yeah, and actually I will cheat here because I will do this only for finite dimensional E. So let's do that. And because you're right, finite dimensional E, that it gets quickly out of hand, and there's not even a agreed definition at the moment of duality of operator systems. I mean, it has to do with the unit, so if that's around or not, but then typically for the dual it will not. So you should think about compact operators and the dual and trace class operators as the dual, for instance, of the compacts. And yeah, so that requires more topological considerations. This is fine for now for us. So these are the maps phi in ED, of course, which map this becomes positive. Okay. So these are I will maybe write this more clearly. So that is the induced order structure, and of course then this is just a sphere essentially in there. So if you know something about the dual, then you know something about the state space. And actually what happens is that you can exchange between a state of E and an array in ED, and it's even better, a pure state of E is actually an extreme ray in ED. So the ray, of course, means you identify all multiples. So that's kind of course, you could take a base, and then you get this norm 1, so that's the state. Extreme is extremal in the convex set of these rays, which corresponds precisely to pure states. So it's a very nice way. So if you would understand a lot about ED, then you can you know what the states look like, and the pure states are of E, because they have an identification of convex sets. And this I will show in some examples. Extreme? So array is just all multiples of some vector in ED. So that's a vector space. You should take all multiples, so that's called array. And that's a convex set. Yeah. Plus, yeah, thanks. Yeah, this one. So it's an array in there, so you take a positive vector and you take all positive multiples of that vector. Then that's a convex set. It's the same kind of argument, and then if it's extremal, so it cannot be written as a convex combination of two, then it's the same as saying it's a pure state of E. Yeah, you're right, so it should be positive. Thanks. So let's put this into action, so we kind of play a little bit with it. So So I will start with, and the example is really quite a treatment. So S1. So I'll spend quite some time on the example. So S1, so I look at the spectral triple of S1. So that's C of S1, acting on L2 of S1. So we go back to the first lecture, I d dx. Okay. So that's my D. And D of Ek, or Ek, happens to be K Ek. So these are like e to the minus ikx, or yeah, that's it. And so what I will now do is I take a spectral projection onto the first n of these. So I take Pn, projects onto the span of E1, En, inside L2 of S1. So it's a finite rank. I have this Cn now, so that's where it acts on. And D will act on this as just, so Pn, this is a matrix, which will now be a diagonal matrix with 1, 2, up to n. Okay, and the rest is 0. So that will be my compressed D, or restricted D. So what happens to this C of S1? That's the challenge. So if I write the function in Fourier, or let's take a single Fourier coefficient, EL. So EL in C of S1. How would that act on L2 of S1? So if I identify L2 of S1 with little l2 of Z, then that's what I'm actually doing when I'm writing such span here. So that's what I get my matrices from. EL will act on this basis given here by a shift, by the amount of L. A shift on L2 of Z. So it will map I, what did I call it? K, I think, yeah. That's why I reserved that, to Ek plus L. And depending on L being positive or negative, it shifts, but it's bilateral. So there's no kind of issue with stars and so on. The star will also do the same, but in the other way, other direction. So this is nice. Now what happens if you shift and cut?
Powers of Jordan blocks. Powers of Jordan blocks.
Yeah, similar, yeah. So you get very nice structure here. So EL, so let's take this one. It will actually be just once on a diagonal which is L away from 0, from the main diagonal. And now, depending on L being positive or negative, it's either here, so this is for positive L, it will be here, 1, 1, and the rest will be 0 again. So everywhere is 0, except on this Lth diagonal. So there will be ones. Okay. And there will be, actually this works also in the other direction, so if L is negative then you would shift the other way, depending on your taste. But because I truncated, this is an n by n matrix. That's because if you truncate and then shift and truncate again, some of these vectors will actually fall out, and that's precisely why you get these diagonals. So in general, if I write a function in terms of its Fourier coefficients, let's take a smooth function. Yeah, L, and then I have, let's say, T or CL, EL. So this is a Fourier series. So you get from Fourier theory. And these EL, again, they just act as shifts. So this means that if you would look at P, N, F, P, N, how it acts on the Hilbert space, then it would act as a matrix where you have C zeros on the diagonal, then you have C1, C1, all the way up to C n minus 1. So they remain constant here. This is C minus 1, C minus 1, up to C minus n plus 1. Yeah.
So this is in the L2Z picture, right?
In the L2Z picture, yeah. Yeah. But not anymore, I project it.
Yeah.
Yeah. So this is on, if you want, yeah, you could say Pn L2Z Pn. So on the span of this thing, which is the orbit space I'm looking at. So these are called Toeplitz matrices. Finite dimensional, so they're n by n. So that's a well-studied object already a long time, more than 100 years they have appeared. And so we will analyze that as well and look at its state space, for instance. Because what we have in mind is that if you now look at the package that we get, we have Pn, C of S1, Pn, acting on Pn L2 of S1, and then you have Pn d Pn, so where this is really just Cn, and this is the matrix that I wrote down there. And they will be Toeplitz matrices of this type. So we denoted this as C of S1 and then n in the top, just to indicate that the dependency on n. So that's it's finite dimensional, so it's closed. It's actually closed under the star because you see it will be symmetric. You just change the role of the C minus with the C plus coefficients. It's also so it is the unit where C0 is 1 and the rest is 0. So it's all kind of well under control. So this can be studied quite well. So I would like, so the task is, can I understand the state space of this, including the metric? So I will not do the metric today, it's just too much, but I will talk about the state space of this one and say something about how it's related to the circle. And I will do that by introducing the dual system. So I will first introduce an operator system and then claim that to be the dual system. So of course I expect this to look like S1 eventually, when n is large enough, so to approximate the circle. So there's a system we call Fégère-Ries, and Riefel picked this up and he calls this Fourier truncations. He actually generalized this from the circle to arbitrary compact quantum groups. So this is the best generalization one can wish for. So it means I take, in this case, but it works more generally, I take C star of Z, which is of course C of S1. This is the convolution algebra on Z, which I take with a finite number of coefficients. So it's like I look at at C minus n plus 1, or maybe I call that A, just to distinguish it from that one, and then A minus n plus 2 to A0, A1, and then all the way up to A n minus 1, and then zeros again. So these are functions on S1 which are finitely supported in Fourier. Yeah. So I put a restriction on what kind of Fourier coefficients I allow for my function, and I say, okay, there's a limit of kind of what I can introduce, and that's the limit which is given by n minus 1. And so the positivity in this system is actually induced. So f is in here. If f is this function f, which is this sum, is positive on S1. So it's a very simple thing. So this function, which is truncated in Fourier, is positive if it's actually positive as a function on the circle, because it's in particular a trigonometric polynomial, okay, with a fixed degree. So that's why I cannot take products, for one thing, but I can say it's positive or not, because it's still a function. So there's no product, not closed under the product. Whereas I should say that there has been a paper, Landi and Lizzi, and should check. Francesco and Andrea was also involved, but it's they do introduce a product on this, but it's not associative. So it's partially defined. So then you could have a product, but the algebra is then not associative. And here I prefer to stay with operator systems, so then this is just what it is, and you look at that. So it's not closed under the product, but it's closed under the star, because the star would kind of move these coefficients to the other side. So this is an operator system, which we called Fégère-Ries, and that's we means Con and myself. Few years back, where we discussed this at length. So we have a lot of computations about this system there. It's a paper in CMP. So what we can now harvest is that there is a sort of well, the first thing is let's see what we can say about this operator system. So can we say something about extreme rays? So yes. So the proposition says that extreme rays in this positive cone are functions, are as sequences like an, such that this anz to the n has all its zeros on the circles. So maybe we should call that, by the way, k, as I fixed my n, sorry. So k is the parameter, running up from minus n plus 1 to n plus 1, n minus 1, and this is just a Laurent series. So you could talk about, and in fact, I think I should shift this. No, it's correct like that. It has zeros on S1.
Sorry, what does the last line mean? So are sequences AK
such that the Laurent series that maps Z in the complex plane to AKZK has all its zeros on the circle. So of course this will have n zeros. Laurent series, yeah. So it will also have poles, but the zeros are all in the circle. I should say actually all zeros. I guess that's clear. So this is something on the complex plane, and it's just a property of the Laurent polynomial, which kind of characterizes that it's extreme. So it's quite surprising that there is such a characterization. It's extreme in the ray of an extreme ray in the positive cone. So that's the first thing. Second is about pure states. On C star of Z n is the pure states are given by all the points of the circle. And so the way to prove such a thing is that you can extend states to a larger C-star algebra, like C of S1. And in fact, you can keep purity as well. So you can extend the pure state to a pure state. You just have to check that you get all of them. Okay? And this is quite nice because this means, so if you take points of S1, so you should be able to sort of distinguish 2 points with your function, with the functions in this class. But if I take n very small, because I didn't say anything about n there, if I take n to be like well, the smallest you can get, non-trivially, which is like 2, then you have a minus 1, a0, and a1 as Fourier coefficients, and all the rest is 0. Which means the functions you have is 1, you have the sine, and you have the cosine. That's all the functions you have available. And no products, just linear combinations of that. And what I'm saying is that with that, you can distinguish all the points of S1. Which if you think a little bit, you can imagine, because you can try to shift a little bit, and so that's okay. Yeah, so then the duality, which I wrote there, is that actually, oh, this may be a bit too much. So the duality is between these two. So the one I had. So there's a pairing between C star S, CS1 n and C star Z lower n to C, which takes a function in here. So it's like this Toeplitz matrix with the z's and so on. C. It was something like k minus L. Yeah. And you take some sequence of that type, A, K. K runs from this to the other. Then what you do is you put them together. So it's like C minus L, AL, and you sum L from minus n plus 1 to n minus 1. So this pairing so clearly it's a pairing which is like a Banach space dual, implementing that because it's finite dimensional, so nothing really spectacular is going on there. But actually this respects the order structure. So this means that if I take an element in here and I consider it what it does on these elements AK, I get a number. And let's say it's positive on all positive elements in there, then this has to be positive. That's what it says. So this is compatible. So it induces actually with the order structure. So this we proved in this paper. And then since we were interested in the state spaces, we only proved, actually we claimed more than we proved. We didn't prove the matrix order, but that was picked up by Douglas Ferencik, who did a very nice paper giving also an overview where he proves that this is actually a duality also at the kind of n by n matrix level. And then you have to do something more than we did. And so that was based on a lemma which Veger and Ries proved, and that's why we call it the Veger-Ries operator system. So the proof is based on Veger. Lemma, which has to do with functions. It's a very nice, so there's many things, and I will probably end also by, so not going to these tolerance relations, if you, I hope you forgive me, but it's just much nicer to actually work through some example in more detail. So this lemma of Veger and Ries, it tells you that if you have a function on the circle with a certain say up to a certain degree, so it's a polynomial, and it's up to some n, so it's a trigonometric polynomial of order n, and you say it's positive on the circle, then you can try to take its square root. And of course, if you're a C-star algebra person, you can always take a square root of something which is positive. But that's not very practical, because it may be a very complicated function now. What this lemma tells you is that you can write it as an absolute value square of a function with half the support. So you can actually find some decomposition. You can take a square root, if you wish, of a function which has this support from minus n to n. And the square is, so the function you're looking for is something like supported here. So that if you take the absolute value squared, you get the whole sequence back. And that's actually their construction. And that's what's driving this, because it allows me to take such a function here and write it as a sort of an absolute value square. And then I get close to what you would call positivity of an operator, because that requires what you noted is that it's h, t, h, and that h will just be that square root. So that's the driving kind of lemma for that proof. And now there happens to be an operator-valued Végieri's lemma, and that's the one that drives Ferencz proofs. So that's, but it's a very elegant. It's simple because it's about circles, but it really works. So
you're actually showing that if you use the Ferencz lemma, you will ultimately get some sort of a trigonometric moment sequence truncated or something like that. In that a n minus l, because that guy has to be positive if you have some truncation of a trigonometric moment sequence, right?
yeah. So if you do you mean this decomposition where you write it as a square, or?
No, I'm saying that this result. So if you use the Ferencz lemma, do you directly show that this t is essentially coming from a trigonometric moment sequence?
It's more about
matrix corresponding to a trigonometric moment sequence, because that has to happen, right? If you have positivity of the Toeplitz matrix, it has to come as it has to be generated by some sort of trigonometric moment sequence.
yeah, that's right. So it's I mean, in the first place, the duality is for vector space not so difficult, of course, because it's finite dimensional. So you get these coefficients. But now, indeed, to put them in a certain form for which the positivity is the one corresponding to this map, that's indeed what you're suggesting. Okay, so we can now sort of flip this proposition around. So maybe put it in here. This is like proposition 1. And it's actually, you could say it's equivalent to this one. It's just the same proposition, because I have this duality, which allows me to move between extreme rays to pure states and the other way around. So this will tell me that the pure states, just copying one by one the line in C of S1n, are, so they're given by, they're labeled by am I saying this correctly? Yeah, by let me actually do it as follows. So they're labeled by endpoints. Endpoints. I should check that n. It's probably n minus 1 on S1. That's because this is actually of degree n minus 1. So there's always this kind of nuisance that you have. So there's actually n minus 1 zeros because that polynomial has that degree. There's Laurent series. And so the n minus points, of course, they do characterize this Laurent series as well. So you can actually go back and forth. So they're labeled by n minus 1 points on S1. And the extreme rays in C of S1 n, they are given by so what I call F lambda. So they're actually like rank 1 vectors. I write them in cat-bra notation, but the main point is that they're labeled by an element in the circle. So that's extreme rays, and these pure states, maybe let's focus on that. So this is like T n minus 1 over S n minus 1. So I know that my pure state space is just n minus 1 elements on the circle up to permutation, because I don't care about the order. And that's actually my pure state space. And this is supposed to sort of approximate a circle. So that's what you kind of should try to have in mind when you want to have this. Let me actually make only some final conclusions about this system, because so it tells me that I have some kind of way to look at points in this truncated system. So now there's one. So there's a result which tells me that if I look at this pure state space, so I call that del E S. So this is. So I just said that's T n minus 1 modulo the permutation group. So if I equip that with the metric, which is actually the one that I was writing all the time, so for these states, I will write this as the supremum over Toeplitz matrices, and then phi applies to T, and psi to T. And I mean, of course, I can use that this is these are matrices. So if I take a pure state, then it, since it again extends as a pure state to the matrices, I know exactly what to do. I know they're given by vector states. So I know that these are actually vectors, and I can write them down. It's not so important to do that here. And they will be labeled by these, so you can parameterize them by these numbers. So there's explicit formulas for that, such that this D, P, N, T is more or equal to 1. Now this metrizes, and one can show the weak star topology on the state space. It also induces a metric on the pure states. And the question is, does this look at all like the limit, which should be something like S1, or maybe the state space of S1? And the result, which, so I have a paper on this, and then also Eva Maria Heckelman has one. A year later, my master's student, but now a PhD in Australia. So what we did was, first I showed that the state space of C of S1 n, so let's call this metric Dn. With the metric Dn, it converges in a sense of Gromov-Hausdorff to the states of C of S1, so the probability measures with the usual metric. And Heckelman showed that this even extends if you only look at the extreme states. So the pure states also do that. To the same thing, okay? So you cannot approximate pure states on S1, so not points. It will always be smeared, but both sequences, Gromov-Hausdorff, converge to that thing. And so the way you should think about this is I have Tn minus 1, and these are like my weights of where some kind of probability distribution comes. And so these points are like the centers of my probability distribution on S1, which you could view maybe as this. So you can kind of have some kind of points on which you find some kind of well, concentration of mass, if you wish, that adds up to the state, the probability measures that I'm trying to approximate. And these will be these points lambda 1, lambda 2, lambda 3. And the only way to get to the pure states is by putting them, say, on top of each other. Then you can make it more narrow and narrow, so that you may be able to do, because here I can also approximate the pure state, but not by allowing all the pure states at the finite level. That will just smear too much because of this phenomena. So that's something. And so what is nice is that if you think about this formula, so this is a supremum of a matrices of some states that you may very well know, of something which is again formulated in terms of matrices. This is just 1, 2, up to n. That's a very simple matrix. So what you can do is this you can do on a computer, and you can, for instance, try to measure the distance that you know on S1, which on S1 between points will be kind of going to pi and then back to 0. Okay, so the distance on S1 has this kind of thing. And what you can show is that since I know it comes close, there's actually plots you can make, and you will find that it kind of approximated rather quickly. So this is n is equal to 3 or something, 5, and so the plots are in the paper. But you see that you quickly kind of, or you get close to the distance on S1, which goes from 0 to pi and back. So you see this as a reflection, but you can just compute it, which is like a sign. So that's what I would like to maybe stress, of that you sort of approximate the geometry that you started with already rather quickly with a finite dimensional system. So it is very rich. And the reason why, for instance, this seems to approximate it more smoothly than if you would take a discrete approximation, which you could also do, you replace S1 by discrete sets like a cyclic group, but then you would lose an S1 symmetry. So the U1 acts here all the time, but my spectral projection actually commutes with the U1. So I know that everything I do is invariant on the U1 transformation. So this is much better than the action of the cyclic group. So that may also imply some equivariance or some invariance of the final result, but it's a discrete group. Whereas I have a U1, which is much kind of giving me much kind of more structure in the end, which looks like a manifold, in this case S1. Okay, I will only indicate what happened in the extensions. So you can also do this for Tn. This is work of Malte, Leimbach, my PhD students. So that kind of approximations. There is also approximations for compact metric groups, which is the paper. So it is of course generalizing this, but then it loses the contact a little with the Dirac operator. So it's more like harmonic analysis. So maybe in terms of a Casimir rather than a Dirac operator. Compact metric groups. That's with Ivan Gaudio Estrada. And in fact, the dual, so this C star of Zn, that also converges in the same sense. So these Fourier truncations also converge. And that is done by Mark Riefel. As I said, extended to compact quantum groups. With I think with some condition. Yeah, so sorry I have no time to also spend on the tolerance relation, but I think it's just too much. But I hope to kind of give you the flavor of where these operator systems appear, and that one should actually try to develop spectral triples and all the theory that we have for something which is an operator system in the first place. Because all the things I was doing, I could have started with operator systems in the first day, because the distance is there, pure states on which I can apply the distance. So everything is captured in this device, and the same axioms make sense. These are just bounded operators. This is again compact resolvent, and this we called an operator system spectral triple. And I guess this is an invitation for you also to further develop this in several directions. But thanks for your attention. I really appreciate it and enjoyed the lectures. So I hope we can still discuss today. But thanks.
So, questions?
What I found it very fascinating, I just wonder, for example, people do lattice gauge theory, where explicitly all the symmetries, translation symmetry, Lorentz symmetry are explicitly broken.
Yeah.
Can such a strategy be adopted in this case also, where Poincare symmetry is preserved?
Yeah, that would be nice. I mean, of course, this. Yeah, I mean, ideally. So, for instance, in all these compact metric groups, so that's the situation is then I am on the metric group, and the symmetry is also given by the same compact metric group. But this could be maybe homogeneous spaces, so it's already somewhat closer to some manifold, like what you're saying. But then the input is really that there is always this group acting, controlling a lot of the analysis along the way, and that's really the driving force of why these classes at least will work. But I guess that could also apply to these situations, except of course that's not a compact group. So there are several kind of steps to be taken, but in principle, so the idea is the same. So that's indeed. Whereas I in fact think that if you, I mean, also these tolerance relations, they seem to behave much nicer with respect to symmetries, because I don't introduce some kind of discretization. I only say, well, these points I don't want to kind of. I cannot distinguish these, but I'm not putting them together in one box or cell. So that's the difference, and that also has a lot of symmetry. Of course, the algebra is much bigger because it's integral operators, so it's maybe more challenging. But the idea is that there's always this invariance around that will kind of help actually to achieve what you want. Yeah, you're right. Yeah.
Any other question? Okay, so if not, so let me ask one. So, so in the proof, what is the precise role of the dual operator system? So you mentioned some results, but
now, so this this is a proposal for a pairing. Okay, so as vector spaces, it's just a duality. So there's nothing special about that. But I'm saying that if T paired with, let me say, let me write the pairing as some kind of bracket. The pairing of T with AK. If this is positive for all AK in the positive cone, this happens if and only if T is positive. That's it. So that's what that's what the theorem claims. So when I say compatible with the matrix order structure, that's what it means. So then I can read off the positivity from this dual pairing, because I have a positivity here, and it induces the one over there. And notice that this is positive as a function, whereas this is positive as a matrix. So it's they're completely different. So if I, for instance, think about these Fourier coefficients, one could say, okay, so if you have this, you have this matrix, which is a Toeplitz matrix. Suppose it's positive. Why don't you just write a function with these Fourier coefficients? Well, that's not a good procedure. So that's not a positive construction in the sense of it will not give a positive function necessarily. And that's actually what Vézier and Ries were looking at. This idea of how can I write from this data something which is actually positive. And you have to do somewhat better. In that case, it's related to the Vézier convolution, so the kernel that you find in Fourier theory. That will actually be a positive map. And that's much better, and it will actually appear in this context as well. But this is the idea. So you have this positivity induced by the pairing, and the other way around, of course. So if this is positive for all t being positive, then the AK will be positive.
So at the heart, you are essentially capturing the corresponding measure of the trigonometric moment sequence. I mean, if mu is the positive measure which produces the moment sequence here, then this guy should essentially come as that integral of mod pz squared times that measure and something along those lines, right?
I think you can formulate it like that, yeah. But I have to check what you have in mind exactly. But because with the moments you mean of what, of t?
Yeah,
The
of
coefficient?
e power tk is integral with some mu, where mu is a positive regular measure.
Mm-hmm. Yeah. Yeah. We can maybe talk a little bit about what you have in mind exactly, so to see.
Any other question? Okay, so if not, so let's thank Walter again for this wonderful series of lectures, and thanks again to the Indian Academy of Science for funding this visit and the series of lectures. Goodbye.